In this video, we are going to derive some equations for residual properties. The original definition of residual properties is something like Mr equal to M minus Miz. M may be any property, something like internal energy, enthalpy, Gibbs free energy. So if you want to calculate residual property, then we can take the difference at the same temperature and pressure. Let me write the first property, that is VR, that is residual volume, and it can be defined in this way: V minus Viz. This is for real gas, this is for an ideal gas. So for real gas, this is the definition of compressibility factor. So from this equation we can write V equal to ZRT over P, and Viz, that is we can take the equation from an ideal gas equation. So that is RT by P, and if we take common RT by P, that is Z minus 1. So this is the first equation of residual volume. It indicates that VR residual, without knowing the value of V and Viz, I can calculate residual volume by Z, compressibility factor. So if you know the value of compressibility factor, then we can calculate residual volume, and this is the one equation. If we talk about Gibbs free energy, then I can write the residual Gibbs free energy, that is G equal to G minus Giz, and if we take the difference, or if we divide by RT, then something like GRT minus Giz upon RT. If you take the difference of dGRT, differentiation of this equation, then we can write in this way: Giz over RT. So this is the equation number 1. We know the definition of dG upon RT. It is something like V upon RT dP minus H upon RT square dt. Right, this equation we have derived earlier, and now I can write the same equation for an ideal gas. Dt. So just properties have been replaced with the V has been replaced by Viz, H has been replaced by Hiz, and then when we can put these two equations in this equation number 1, so it would be dGr over RT equal to V upon RT dP minus H upon RT square dt plus Viz over RT, because it is minus sign, so RT dP, and this minus minus plus, that is Hiz over RT square dt. And if we take the difference between these two, dGr over RT, it would be V minus Viz, so that is Vr over RT dP. I have taken the difference between these two. The other terms are common, only V minus Viz. Same thing here also we can write, that is Hr over RT square dt. So this is the equation of residual Gibbs free energy change. It is in differential form. Okay, so this is just relation of Gr with Vr and Hr. In this equation, if I consider constant temperature, then I can take this equation as a partial derivative also, something like del Gr over RT with respect to del P at constant temperature, this versus with respect to del means the pressure at constant temperature. So it would be Vr over RT, and the other equation would be del gr over RT with respect to del T at constant pressure, that is equal to minus HR upon RT square. Equations we have done earlier also. Now the next question is these two equations. If I take the temperature constant, then dGr over RT, it would be something like, this term will be cancelled out and this would be VR over RT dP. If I integrate this equation, this is for constant temperature. If I integrate this equation from pressure equal to 0 to pressure equal to P, then it would be GR over RT equal to 0 to P VR upon RT dP. I have not written the integration constant. We can write the integration constant, but always when we are going to calculate the change in the property, constant term, integration constant will be cancelled out. So I have not written. The other thing is VR over RT, that is something like RT by P Z minus 1. So GR over RT, that is 0 to P, and VR over RT, that can be Z minus 1 dP by P. This is very important equation for any type of exam, or as for example even for GATE exam. GR over RT, that is 0 to P Z minus 1 dP by P. If you know the value of compressibility factor, then you can calculate GR over RT. It means you can calculate residual Gibbs free energy. Okay, so that is the one thing. In other case, I can calculate the HR over RT also by taking the differentiation of this term. So it is something like HR upon RT equal to minus T, the partial derivative of this entire term with respect to temperature and keeping pressure constant, means the partial derivative of this integration. So it is the differentiation of integration with different variable. Here integration variable is P, but here derivative variable is T. So both variables are different, and to solve this equation, there is one mathematical concept, that is Leibniz rule, from where you can calculate the differentiation of integration or integration of differentiation. So I am writing the final equation, HR over RT equal to minus T, that is something like del Z over del T at constant P dP by P and 0 to P. So this is the equation of HR over RT. I have not calculated, I have just shown the Leibniz rule to do some calculation, something like integration of differentiation or differentiation of integration, and this is the final equation of HR over RT. Means if you know the value of Z, then you can calculate the value of GR. If you know the value of Z, then you can calculate the value of HR. If you know the values of these two, G and H, then also you can calculate the value of SR, because G equal to H minus TS. So I can write the same equation in this way also, SR. So if you know these two values, then we can calculate SR also, means the residual entropy. The other thing is, in this equation, it is little bit confusing. You might be thinking that here P is constant and here integration variable is P, so it should be 0. No. How it is applicable? It is something like, if you have a data of Z versus temperature, so you have data versus temperature, Z at temperature at one pressure, right? These are the different values. So just plot the Z versus T at constant pressure and find out the slope of that curve at constant pressure. So that is the one value of this derivative. At other pressure, again the value of Z and temperature would be different. So again you will plot another Z versus T and find out the slope of that curve, again you have the other value. So this derivative has different values at different p. Different values at different p means that if your p is different, then this derivative has different value, and those values have been integrated using this integration. So these two, this is very important, means you should remember this equation gr upon rt 0 to p z minus 1 dp by p. So if you know the value of z, then, or if you know the equation of z, then you can integrate and you can calculate gr over rt. Similarly, this is another equation of hr over rt, and the third property, that was Vr equal to rt by p z minus 1, and you can easily calculate sr if you know the value of gr and hr. Thank you. Thanks for watching this video. Please subscribe to my channel.